In this lecture, we'll take a look at the elementary matrices. There are 3 of them, and they are typically called the swap matrix, the scale matrix, and the pivot matrix. So let's begin with the swap matrix. To get a swap matrix, you start with the n by n identity matrix, and then you swap 2 arbitrary rows. Here is I4. And by the way, I have switched to RStudio, which I find more user-friendly. If you want to download it, you'll find it at rstudio.com. So if I start with this matrix and I swap any 2 rows, let's say I swap row 2 and 4, then I'll get this matrix where you can clearly see that row 2 of my swap matrix is 4 of my identity matrix, and vice versa, 4 is 2 of my identity matrix. Here is the same example. The swap matrix is also called an elementary matrix of type 1. And for notational purposes, I will denote this by E, which is for elementary matrix, followed by a 1, which tells us that it's a swap matrix or an elementary matrix of type 1. I use a semicolon followed by n, which is the number of rows, also the number of columns of my swap matrix. And then I'm going to use 2 indices I and I prime, which will be the rows that I swap. So in the example above, n is 4, so 4 by 4. And since I've swapped rows 2 and 4, I'm going to call this E1 semicolon 4 2, 4. The swap matrix has some really nice features, which we see if we multiply an arbitrary matrix by a swap matrix. So here is my swap matrix E, where rows 2 and 4 have been swapped, and an arbitrary 4 by 4 matrix A. If I pre-multiply A by my swap matrix, we see that the effect will be to swap rows 2 and 4 of A. You can see that E times A, the second row, is the 4th row of A, and the 4th row is the second row of A. And this is true for any swap matrix. For example, if I create a swap matrix A swapping rows 1 and 2, then E times A will swap rows 1 and 2 of A. If you post multiply by a swap matrix, the effect will be the same but for the columns. Now compare this to A and you clearly see that columns 2 and 4 have been swapped. In the example, A was square, but that's not necessary. A can be any matrix. For example, when I did this here, E times A could be any matrix as long as the rules for multiplication is satisfied. So my E had 4 columns, which means that A must have 4 rows. But it could have 6 columns, for example. It would work just the same as well. Same when I post multiply by E, A could have been, for example, 6 by 4, and the result would have been the same, switching columns 2 and 4. And so here is the result. If A is an arbitrary n by m matrix, then E times A will be a new matrix equal to A, but where rows I and I prime of A have been swapped. Similarly, if you post multiply, then since the dimension of A is n by m, E must have m rows, and the effect will be to swap columns I and I prime of A. And here's one more example. E is 3 by 3 swapping rows 1 and 2, and A is a 3 by 3 matrix. Then pre-multiplying by E will swap rows 1 and 2 of A, while post multiplying by E will swap columns 1 and 2 of A. It's not hard to prove, but just a little bit messy. You should convince yourself that this actually works by computing these products E times A and A times E by hand, and by doing this you'll realize exactly why multiplication will swap rows or columns. The next elementary matrix is called the scale matrix. The scale matrix also starts with an arbitrary identity matrix. It then changes one of the diagonal elements into a number different from 0. So here's a scale matrix where we have taken the second diagonal element and changed that from a 1 to a -3. Repeating, by multiplying one of the rows of the identity matrix by, and this is important, a non-zero constant. That will give you the scale matrix. You're not allowed to change one of the diagonal elements into 0. Here's the example again. The scale matrix is also called an elementary matrix of type 2. The notation we use for the scale matrix is then as follows. E parentheses 2 to tell us that it's a scale or a type 2 matrix, semicolon, n tells us how many rows and columns, I tells us which row of the identity matrix that we will make the change, alpha is the constant that we will replace 1 with. In the example above, n is 4, we're making the replacement on the second row, so I is 2, and we're replacing 1 with -3, so alpha is -3, and the matrix is E2, 4, 2, -3. Here's the scale matrix again and an arbitrary matrix A. If I pre-multiply A by a scale matrix, we can clearly see what happens. It's only the second row that's affected, and what happens is that every element of A will be multiplied by -3. So this 3 will go into -9, 0 to 0, 4 to -12, and 9 to -27. Post multiplying by a scale matrix will similarly multiply the entire column 2 by -3, as we see here. If A is an arbitrary n by m matrix, then pre-multiplying by E will scale the entire row I of A. That is, will multiply every element of row I of A by alpha. Post multiplying by E will scale the entire column I by alpha. Here's another example. E is 3 by 3. I have scaled the first diagonal element and the scale factor is 2. And so taking A to be this matrix, pre-multiplying by A will multiply the entire first row by 2, while post-multiplying by A will multiply the entire first column by 2. The final elementary matrix is the pivot matrix. Here, again, we start with the diagonal matrix. For the pivot matrix, instead of replacing one of the diagonal elements, we replace one of the off-diagonal elements with a number. For example, this is a pivot matrix where I have replaced row 2, column 4 with the number -2. For the pivot matrix, you're not allowed to change the diagonal elements. You are, however, allowed to use the number 0, even though it's kind of pointless because that will just give you the identity matrix. To review, replacing a single off-diagonal element of the identity matrix with a constant, any constant, will give you the pivot matrix. And here's the example again. And the pivot matrix is called the elementary matrix of type 3, the final one. The notation we use for pivot matrix is E parentheses 3 to tell us it's a pivot or a type 3 matrix, semicolon, N is the number of rows, I and J is the row and the column of the off-diagonal element that we replace with alpha. And it's important in this case that I cannot be equal to J. The example above has n equal to 4. I have replaced the element in the second row and the fourth column, so I is 2 and J is 4. And I have replaced it with -2, so alpha is -2, and the notation for that example is then this. When we do multiplication with the pivot matrix, the result is slightly more complicated than the swap and the scale matrix. To see the effect, I start with a slightly simpler pivot matrix where the constant is 1. If I do E times A, the result might at first not be completely obvious, but the first thing we see is that it's only the second row that's affected. This is because the non-zero off-diagonal element is in the second row of E. Second, we can see that the second row of this product is precisely the sum of the second row and the fourth row of A. 3 plus 1 is 4, 0 plus 8 is 8, 4 plus 1 is 5, 9 plus 7 is 16. The reason that we're adding the fourth row to the second row is really because the off-diagonal element here of E is in the fourth column. Had this 1 instead been here in the third column, the effect would be to add the third row of A to the second. So we can conclude the following. The product of E times A will be the same as A with the following change. Row 2 will be affected simply because the off-diagonal element is in row 2, and it will be replaced by the sum of the second and the fourth row because this is in position 2, 4. So let's consider a slightly more complicated case where I have a -2 in position 2, 4. Again, it's only the second row that's affected, and the second row is now equal to the second row of A. Add to that -2 times the fourth row of A. So this element here, 1, that's 3 minus 2 times 1, so that's 1. Minus 16, it's 0 minus 2 times 8. 2 is 4 minus 2 times 1. And minus 5 is 9 minus 2 times 7. Post multiplying by E will lead to a similar result. In this case, it'll now be the fourth column of A that will be replaced. And the fourth column of the product will simply be the fourth column of A minus 2 times the second column of A. So let's review these results. If A is an arbitrary n by m matrix and I pre-multiply by a pivot matrix, then that will give me a new matrix n by m with the following change. All rows of this product will be the same except for the ith row. It's only the ith row that will change. And the ith row of the product will be equal to the ith row of A plus alpha times the jth row of A, like this. Post multiplying by a pivot matrix is much less important. It's the pre-multiplication that you should learn. But post multiplying by A will have the following effect. All columns except the jth column will be the same as A, and the jth column will be replaced by the jth column of A plus alpha times the ith column of A. And here are some examples. So let's say that my pivot matrix is 3, 2, 1, minus 1. So remember, that's the 3 by 3 identity matrix where I have replaced the element in row 2, column 1 with minus 1. And A is this matrix. Pre-multiplying by E will then replace the second row of A, and it will be replaced by the second row of A subtracting the first row of A, like this. So simply take the second row of A and subtract the first row, and you get E times A. Post multiplying by A, doing A times E, will now affect the first column of A. And the first column of the product will be equal to the first column of A minus the second column of A. So it'll be this. And again, it's E times A that you should really learn how to do. A times E is not that important.